Hi guys, today we're going to continue our discussion about the thermodynamics of ideal gases. And on this video, we are going to talk about the isobaric process. And as you have learned to our previous video, when we say isobaric process, we are talking about a constant pressure process. So again, we will be discussing the equations that we will be using when we are solving ideal gases in constant pressure process. Okay, so you can see here our derivations for the equations, and then we will be solving 3 problems, and these problems would be really helpful kasi it applies a lot of informations na na-discuss natin sa ating lecture video. Okay, so as you can see, we have our first problem here in which we need to determine our change in enthalpy, and then our second problem in which we calculated for heat, work, change in internal energy, and the change in enthalpy. Then finally, we will be solving a problem in constant pressure, but our CP is not constant. Okay, so far, as you have seen on this video, no, and in our lectures, that we are using constant CP in here. Okay, but there are cases like this problem in which our CP is not constant but rather determined by this equation. So we will be solving for our heat and our delta H by integration. Okay, so this will be really interesting, and I hope that this video would help you in your study about the thermodynamics of ideal gases, no, in isobaric process. So hindi na natin patatagalin pa. Let us now jump to our discussion. When we say that we have an isobaric process, we mean that our process is operating under constant pressure. Therefore, isobaric process means that we have a constant pressure process. Okay, so therefore, our pressure is constant, okay, when we have an isobaric process. Of course, we learned from our general chemistry course that if we have an ideal gas operating under constant pressure process, we are using the Charles law. And according to Charles law, our initial volume over our initial temperature is equal to our final volume over our final temperature, where our temperature is expressed in unit Kelvin, right? And for heat and isobaric process, we actually learned this in a separate video about heat, that as per definition, our heat at constant pressure is equal to NCP delta T. Or we could also write this at NCP T2 minus T1, where CP is our specific heat capacity measured at constant pressure. Okay, so this is the equation that we are using in finding heat at constant pressure. And then for internal energy, of course, we could still use our equation for the first law of thermodynamics, in which delta U is equal to Q plus W. Okay, so you could learn more about this if you check our video about the first law of thermodynamics. And then we also learned that delta U is equal to NCV dt, right? Where we could also write this at NCV T2 minus T1. Okay, where CV is our specific heat capacity measured at constant volume. Okay, so this is the equations that we will be using in finding for the internal energy. Now let's go for the enthalpy. So in a separate video, we learned the essentials, okay, what we need to learn about enthalpy. And by definition, we learned that enthalpy H is equal to U plus PV. And this is a state function, right? So we learned from our video that delta H is equal to delta U plus P delta B. So the reason why we do not have delta PB here, because we have a constant pressure process. Okay, that is why we have delta H is equal to delta U plus P delta V. Okay, now we learned that in our first law of thermodynamics that delta U is equal to Q plus W, right? So therefore, we could substitute these equations in here, okay? So we could replace this delta U by Q plus W. So we have delta H is equal to Q plus W plus P delta V, okay? And we also learned in a separate video about work that work is equal to negative P delta V. So we could replace this W here, right, by using this. Okay, so therefore we could have delta H is equal to Q. Then replacing W by negative P delta V, we have negative P delta V plus P delta V. So as you can see, this one will be equal to 0. Okay, negative P delta V plus P delta V, that will be equal to 0. So therefore, our delta H is equal to our heat at constant pressure, right? So delta H is just equal to Q at constant pressure, but our Q is equal to NCP delta T. Therefore, our delta H could also be written as NCP delta T, or can also be written as NCP T2 minus T1. Okay? And now let's go to work. Okay, so as we have shown earlier, our work is equal to negative P delta V. Okay, which we could also write as negative P V2 minus V1. Okay, so we could use this already in finding the value of work. Okay, but since we know that we are working with ideal gas here, therefore, we could also use our ideal gas equation, in which we know that PV is equal to nRT, right? In which, for the initial condition, let's say our initial pressure, initial volume, this is equal to nRT1, our initial temperature. And then, for the final condition, we have our P2, V2 is equal to nRT2, right? So this will be our initial condition, and this is our final condition. Now, what would happen if we subtract our final condition with our initial condition? So we will have P2 V2 minus P1 V1. So we will have here P2 V2 minus P1 V1, which is equal to nRT2 minus nRT1. Okay, but we are operating here at constant pressure process. So therefore, our P2 is equal to P1, right? So P2 is equal to P1 because we are in constant pressure process. So therefore, we have P, then V2 minus V1. Okay, so we just factor out P because it is constant. Then we have here our NR will not change, so we will factor that out. So we have NR times T2 minus T1. Now, as you can see, PV2 minus V1 is the same as this one. So therefore, we could replace that to get the value of work. So our work is equal to negative P times V2 minus V1, which is also equal to this, which is NR T2 minus T1. Okay, so these are the equations that we will be using when we are processing an isobaric process. Okay, so in order to apply that, let us try to solve some problems in isobaric process for ideal gases. Okay, so starting with problem number 1. Nitrogen behaving as an ideal gas undergoes a temperature change from 300 Celsius to 120 degrees Celsius. The specific heat at constant pressure is 1.04 kilojoule per kilogram per Kelvin. Determine the change in enthalpy per kilogram of nitrogen gas. So, as you can see, we have given here the initial temperature and the final temperature. So, our initial temperature is equal to 300 degrees Celsius, and our final temperature is 120 degrees Celsius. Of course, we are working with ideal gases, so we need to convert this to Kelvin, right? So we need to add 273.15. So this will be equal to 573.15 Kelvin. And then we have here 120 plus 273.15. So we will have 393.15 Kelvin. Okay, we also have here the specific heat at constant pressure. So we have our Cp, which is equal to 1.04 kilojoules per kilogram Kelvin. Okay, so we need to determine the change in enthalpy. So we are looking for delta H. Okay, so we know that the formula or our equation for delta H is equal to NCP delta T. Okay, so as you can see here, okay, because this is equal to heat, which is NCP delta T. Okay, but we will not be using N here. Okay, as you can see here, we have N. We will not be using that because we are required to determine the change in enthalpy per kilogram of our nitrogen gas. That is why our Cp is already expressed in a unit in which our denominator is already having kg, right? So therefore, our delta H will be Cp delta T, or Cp times T2 minus T1. Okay, so our delta H is equal to our Cp, which is 1.04 kilojoules per kilogram Kelvin, times our temperature. Our T2 is 393.15 minus our T1, which is 573.15, and this is in Kelvin. So checking our unit for Kelvin will be cancelled out. So our answer here will be in kilojoules per kilogram. Okay, so therefore our delta H will be equal to, let us solve for this. We have 1.04 times 393.15 minus 573.15, okay, which is equal to negative 187.2. So we have here negative 187.2 kilojoules per kilogram of nitrogen gas. Okay, so this is our final answer to our first problem. Okay, so now let us go to our second problem. We have 3 moles of an ideal gas with Cp, which is equal to 7/2R, which is heated at constant pressure from 45 degrees Celsius to 50 degrees Celsius. So we need to calculate the heat, work, the change in internal energy, and the change in enthalpy. Okay, so, well, I could see here that there is very small difference, no, in our temperature. So it's better, no, para mas makita natin yung difference, let us change this to 25. I think it will be better to calculate it this way, no, because with only small difference in temperature, I think we will not be able to see what is really going on here in our problem. So let's change it to 25 to have our values significant, no? So let us write all our given information. So we have 3 moles of an ideal gas. So therefore, our N is equal to 3 moles. And then we have our initial temperature, our T1, which is equal to 25 degrees Celsius. And our final temperature, which is 50 degrees Celsius. We also have our Cp here, which is equal to 7/2 of R. Of course, we need to change this to Kelvin because we are working with ideal gases. Okay, so let's say here's this one. Let's say we'll add 273.15. So we have 298.15 Kelvin. And here we have 323.15 Kelvin. Alright, now, so we could start solving for our required here. So, as you can see, given ang ating CP, temperature, and number of moles. So, therefore, it will be easy to calculate for the change in enthalpy. We already used this in this previous problem, no? So, our delta H is equal to N CP T2 minus T1. So let us just substitute our values here. So our N is equal to 3 moles. Our CP is equal to 7/2 of our R, the universal gas constant. Since we are in Kelvin and in moles, so we could use 1.987 calories per mole Kelvin, right? And then for our delta T, we have 323.15 minus 298.15 Kelvin. So let us check first our units. As you can see, our number of moles will be cancelled out and unit Kelvin will be cancelled out. So ang may iwan sa atin dito will be the unit calorie. Okay, so let us now calculate for the delta H. We could use our calculator here. So we have 3 times 7 divided by 2, okay, then times 1.987, then we will multiply this to our delta T. So we have 323.15 minus 298.15, and this is equal to 521.59. Okay, so we have 521.59 calories. Okay, so we already got our delta H. Okay, so we still need to get delta U, W, and Q. Okay, well, we already learned here that at constant pressure process, our delta H is equal to our Q. So therefore, we could write here our Q at constant pressure. This is also equal to our delta H, which means this is also equal to 521.59 calories. Alright, so we already got 2 of our requirement. Okay, so the next requirement that we will try to solve is our change in internal energy, and we know that this is equal to N CV T2 minus T1. Okay, so we already wrote this earlier in our lecture, so we don't know what is the value of CV, but we already discussed in our lecture about specific heat capacity that we have a relationship between CP and CV. We know that our CP minus CV is equal to R, right? But we know our CP here. Our CP is equal to 7/2 R. So we could substitute that here. So we have 7/2 R minus CV is equal to R. So therefore, our CV is equal to 7/2 R minus R. Okay, so our CV is actually equal to 5/2 R. Okay, so solving on this one by fraction, So now we could use that here in our equation for internal energy. Therefore, I'll just write it here. Now we are losing some space in here. So we have our delta U, which is equal to N CV T2 minus T1. Okay, so our N is equal to 3 moles. Our CV is equal to 5/2 R. So we have 5/2 times our R, which is the same as this one, 1.987 calories per mole Kelvin, times our delta T. Okay, so we don't have space here, so I will just write this one. So we have 323.15 minus 298.15 will be 25 Kelvin. So we have 25 Kelvin. So therefore, our units here will be cancelled out. So our moles will be cancelled out. Our Kelvin will be cancelled out. So now we can calculate for the value of our delta U. So our delta U will be equal to, so let's me calculate that. So we have 3 times 5 divided by 2, then times 1.987, then times 25. Okay, so we have 372.56. So 372.56 calories. Okay, so we already got the value of delta U. Now, the remaining requirement is the W. Now, we need to determine the value of W. There are two ways to calculate for our W. We could either use the equation for the first law of thermodynamics, because we already know the delta U and we already know the value of Q. So, therefore, we can calculate for W. But on this case, I will use this equation here. W is equal to nRT2 minus T1, okay, in order to show you how to use that. So we have here our W, or let me write that in white. So we have our W, which is equal to negative nRT2 minus T1, okay. So our W is equal to negative 3 moles, okay, times our R. Our R is 1.987 calories per mole Kelvin, times T2 minus T1, our delta T, which is 25 Kelvin. Okay, so let's check our units. So our moles will be cancelled out, Kelvin will be cancelled out. So now you can use our calculator for solving the value of our W here. Okay, so we have 3 times 1.987 times 25. Okay, so we have 149.025. Okay, so we have negative 149.025 calories. Okay, so now we already got all the requirement for in our problem. We solved for Q, W, delta U, and delta H. So let us now go to our third problem. The specific heat at constant pressure of a gas is given by Cp, which is equal to A plus Bt plus Ct squared, which is in kilocalories per kilogram per Kelvin, where A is equal to 0.216, B is equal to 0.00001, C is equal to 1.287 times 10 to the negative 8, and T is in unit Kelvin. Find the amount of heat required to raise the temperature from 100 degrees Celsius to 2000 degrees Celsius. Okay, so our given here is the initial and final temperature. So we have our T1, which is 100 degrees Celsius, and our T2 is 2000 degrees Celsius, and also our specific heat at constant pressure. It is given by this equation, which is A plus Bt plus Ct squared. Okay? And of course, given yung mga values ng ating ABC in here. Now, we need to find the amount of heat required to raise the temperature from the 100 degrees Celsius to 2000 degrees Celsius. So, we are looking for the value of Q at constant pressure here, right? And we know that at constant pressure, this is just equal to our delta H. And this is equal to Ncp dt. Well, the reason why we have the equation delta H is equal to Ncp T2 minus T1, well, it is because if you take the integral of this one, okay, and our Cp is constant, okay, if the Cp is constant, so this will just be equal to Ncp T2 minus T1, if this is from T1 to T2, okay. So if you take the integral of this, our N and Cp are constant, so we will just be taking that out. Then the integral of dt will be t. So this is an definite integral. So this will be t2 minus t1. But in this case, our Cp is not constant. It is given by this equation. So therefore, we cannot use this equation. No? We cannot use this because our Cp is not constant. Okay, so what are we going to do in order to solve this problem? So we need to actually calculate for the value of delta H, but our Cp is not constant. So therefore, we need to take the integral of our equation in here. So we have our delta H is equal to the integral of NCP dt. Okay, but our Cp in here is already expressed in per kilogram unit, no? So therefore, we will not need our N in here. Okay, so therefore, we will be taking the integral of Cp dt from T1 to T2. Okay, but to do that, we need to express our Cp as a function of temperature, in which we already have here. Okay, so let us substitute that here. So we have our delta H, which is equal to, from T1 to T2, then our Cp is A plus Bt plus C T squared dt. Okay? Okay, so let me just move that here, no? Kasi medyo ginigipit tayo ng space na naman eh. So we have delta H is equal to, now I'm going to distribute this, no, as per our properties of integral. So we have from T1 to T2, we have A dt, then plus from T1 to T2, we have Bt dt. Okay, then plus the integral from T1 to T2, we have C T squared dt. Okay, and our A, B, and C are all constant, so we could just take that out. Okay, so let me write that para hindi malito yung ating mga viewers. So we have A from T1 to T2 dt, then plus B, the integral from T1 to T2, we have T dt, then plus C, the integral from T1 to T2, we have T squared dt. Okay, so let us now solve for the integrals. Okay, so we have delta H is equal to A, the integral of dt, which is t, and this is from T1 to T2, plus B, the integral of t dt will be t squared over 2, and this is from T1 to T2, then plus C, the integral of t squared dt will be t cubed over 3, and this is from T1 to T2. Okay, so again, our T1 is equal to 100 and our T2 is equal to 2000. So therefore, now we could substitute that. So we have delta H is equal to A, then our T will be T2 minus T1 plus B over 2, then we have T2 squared minus T1 squared, then plus C over 3 times our T2 cube minus T1 cube. Okay, so we'll be substituting this. Okay, however, we need to express this in Kelvin. Okay, because as you can see, our Cp is expressed in unit Kelvin, no? So plus 273.15, so this is equal to 373.15, then plus 273.15, we have 2273.15. Okay, so now let us use that here. So our delta H is equal to our A. Okay, so let us substitute na lahat ng ating value. So our A is equal to 0.216. Okay, so we'll write that here. 0.216 times our T2, which is 2273.15, minus our T1, which is 373.15, and this is in Kelvin. Okay? So, anyway, let us remove our units. Okay? Because anyway, we know that the answer will be in kilocalories per kilogram because we are multiplying temperature in all of our terms. Okay? So, plus our B over 2. So, ano nga ulit yung value ng ating B? Our B is 0.0001. Okay? So, we have our B, which is 0.00001 divided by 2 and multiplied to our T2, which is 2,273 squared, okay, minus 373.15. No, I'm not writing the decimal. 0.15 squared, okay? And then this one plus our C, okay, our C is 1.287, okay, 1.287 times 10 to the negative 8. So 1.287 times 10 to the negative 8 over 3. We have denominator 3 here. Do not forget that. So we have our T2 cube. So our T2 is 2,273.15 cube minus our T1, which is 373.15 cube. Okay? So now we can solve for our delta H. Okay? So medyo mahabang solution. So let us now start to solve it. Okay? So 0.216 times our delta T. We have 273, 2,000, I mean, sorry. We have 2,273.15 minus 373.15. Okay, so this is equal to 410.4. Okay, so I think it's better na isulat ko na lang. 410.4. Okay, then plus our next term dito sa nasa itaas. Okay, so ginagawa ko to guys para makita ng mga viewers natin kung paano natin nakuha yung mga values. So 0.00001 divided by 2 times, okay, we have 2,273 squared, 0.15 squared, then minus 373.15 squared. So this is equal to 25.14. So we have 25.14 in our second term. Now for our third term, ito, yung naka-cube. So let us solve it now. We have 1.287, then exponent negative 8. Okay, divided by 3. Then times our difference here. We have 2,273.15 cube minus 373.15 cube. Okay, and this is equal to 50.167. So we have 50.167. So therefore our delta H is equal to, let us try to solve it now. We have 410.4 plus 25.14, then plus 50.167. So this is equal to 485.7. Okay, so 485.7 kilocalories per kilogram. Okay, So this is also equal to our heat at constant pressure, which is 485.7 kilocalories per kilogram. Okay, so this is our final answer to problem number 3. Okay, so medyo mahaba yung ating mga solution, pero I hope that it helped you, okay, in your study sa ideal gases in thermodynamics, and this is about isobaric process, no? So I hope this helps. Thank you very much and have a nice day. To watch more of our lecture videos about engineering and STEM subjects, please subscribe to our YouTube channel and click on the notification bell para lagi kayong updated sa mga videos na i-upload namin. We are regularly uploading tutorial videos in engineering, mathematics, chemistry, physics, at iba pang subject na magagamit ninyo sa inyong pagre-review. So, thank you very much sa patuloy ninyong pagsuporta sa enginerds.org.